dimension. Please? Yes? Okay. Tak, I must return. Tak, I must go back. So here the last sentences is problem with my mouse. For global transformation, insufficient Alven velocity. So the solving may be filamentary structure. First publication about filaments observed if PF1000 are presented in this paper. For this diagnostic, we use a small pinhole, 1 millimeter pinhole, and one from pictures, from interferometric pictures. And in this case, we observe filamentary structure in some regule. First, filaments are observed in surface of the dense column. Second type of filaments is in lobule, in places where the plasma is ejected from the column. They are observed in formed and decaying structure. They are observed in a region where we observe connection of a few structures. Interesting is that we didn't observe filaments in plasmoids, probably due to high density, where the density gradient are very low. The detail, the filament in the surface of the column, we see in these double pictures. Interferometer and Schlieren are taken in the same moment, in the same position. It means the structure is observed in very thin layer on the surface, and its structure is mosaic-like. It has irregular direction. In this slide, we see nice filaments which are formed in the lobules, in the areas where the plasma is going from the dense column. The length is 1 millimeter, diameter about 200 microns. And here, this part is on the boundary of the dense column, with this evident filamentary structure. In this slide, we see interesting filaments in the areas in the dense column when we have connection of two structures, for example, in this case or in this case, connection of top of two plasmoids. So in this slide, we see connection between filaments and sources of fast particles. The sources of fast particles, of fast neutrons, was observed in pinhole camera, and they are seen as the very small point sources. How interpret the filaments? We interpret them as it is areas with high plasma density caused by pinch effect of the flowing current, is very high density. The filaments exist in areas of the current, and what is interesting, they have probably scenario from the layer to the filament and transformation of filament into blobs. It is similar analogy as the waterfall. In this case, no surface tension, but Maxwell longitudinal tension, which can form this tearing also. So, possibility of interpretation of evolution of filaments on the basis of internal current and accompanied magnetic field, which may be the way how to obtain the small sources of fast neutrons. Conclusions. That we can conclude that filaments exist in shots with only pure deuterium filling. Dimensions filaments diameter in the order 100 micron with length 1 millimeter, 1 centimeter. The density gradients is between 10 to 24, 10 to 25 if in a cubic meter. They are registered in areas of the measured currents or transforming structures. They are recorded also in the boundary between dense and rare plasma. Interpretation probably is that they are formed by that plasma. In plasma foci has filamentary structure, and filaments can be interpreted as the current filaments. It may be connected with existence of localities with 100 Tesla and high pressure of megaamperes. Second publication was from experiments which were done in small plasma focus in Czech Technical University. And here we use very fine diagnostics, refractive diagnostic with Schlieren method, and second method using Wollaston prism. It is a special part of differential interferometry. The density is similar 10 to 24, 10 to 25, and special sensitivity is in the order 40 micrometers. And the shot has similar evolution as usually plasma focus, implosion of the current cheese, formation of the pinch, and evolution of instabilities. In Schlieren diagnostics, it seems very interesting because we can compare the four figures. Two figures from Schlieren method and two figures from differential interferometry method in the same position, in the same shot with time delay 5 nanoseconds. Here we see interesting configuration formed by small azimuthal filaments. which longer lengths, for example, in this case, when we see practically filaments along the total azimuthal length. Here we see also this fine structure in perpendicular direction. At this Schlieren scale, we don't see the axial filaments. The axial filaments has probably lower density because we see it in low deflections. So in this high resolution, we see only the radial filaments. Next time is seen here. We see formation of the azimuthal thin filaments. We see also formation of the filaments axial on the boundary of the column. And what is interesting is the axial part of the dense pitch, which is very thin and very dense. Its density 10 to 25, diameter about 200 microsecond. And this structure is formed regularly in each pinch. This structure isn't seen in PF1000 in interferometry picture, probably due to small refraction. We see sometimes it in the on the XUV frames. Next, next it is similar part. We see once more the axial filaments in the surface, and we see once more the central dense cord, cord, in which side we can observe filamentary helical structures. The later phase we see in this slide at high neutron yield, we see formation of the structures with usually filamentary structure in the boundary, with ejection of to the radial direction, and it is at the same time. And later, after 5 nanoseconds, we see explosion during hot X-ray neutron production, radial explosion of the plasma. We see that this explosion is connected with the localities where we observe ejection of the plasma out from the pinch. In the next slide, we have difference. In short, we have very low neutron yield. In this case, we observe very nice compact structure, once more 2 or 3. And we see they high stability during 5 nanoseconds, practically didn't change. But interesting is that the cord in the center has higher diameter, and this discharge differs from the high neutron yield due to slow evolution. Here we see once more filamentary structure, once more wide central cord, and during explosion, we see the decay of structures, but in this case, it is slower and part by part. No ideas. It is idea of Bostick, where we suppose existence of colloidal closed current in the plasmoidal structures. with central cord. It's very interesting for Z-pinch and plasma focus because in this case, this boundary is diameter of the dense column, and in this part is in the center. It means that in case of this model, we find here locality with magnetic field 100 Tesla and megapascal pressure. Another idea is plasmoid in a plasma with slow beta, where it's concentrated from the force-free current and magnetic structure. But I remember experiments of Slava Kraus, experiments which were done in PF1000 and in PF3 in Kurchatov, where they observed the use for better visualization, admixture of neon, and they try to put the probe in the center of the structure, and they can measure the distribution similar to plasmoidal distribution of the current. The next case which is important to study in future is plasmoidal structure, which is formed from two conical electrode, cathode and cathode, which form near the top of electrode the jets, which accelerate plasma to the center and form here one plasmoidal structure in Z-pinch discharge. Now, in this case, I only mentioned the project Czech Polish, which we upload this week. Its name is Dynamics of Dense Plasma Structures Generating Strong Fields and Energetic Particles from Ball lightning to inertial fusion. And here is picture of three shots in plasma focus in PF1000, where we see in one shot formation of the toroidal structure and transformation to the plasmoidal structure in dimension about 1 centimeters during time 40 nanoseconds. The second example, similar transformation, plasmoidal, toroidal to plasmoidal, we observe in a laser system pulse when we concentrated the laser beam on the foil. In this case, it was plumbum. Here also form in form of the discharge toroidal structure, which form plasmoidal structure, but in another scale. In this scale, the dimension is about 100 micron, and time scale is 100 picosecond. And second example is National Ignition Facility, when we take the neutron source, its evolution during time from 2014 to 2021. In the first experiment, the neutron source has toroidal structure. In later experiments, at a higher neutron yield, it was spherical structure. And in last shot, when we observe ignition, when we have very high neutron yield, it is practically structure similar to plasmoid in high density. So, conclusion of my lecture. So we see existence of filamentary structure in pure deuterium plasma. Filaments can have not only axial direction, but also azimuthal direction. We can give assumption about current base, about this origin. What is important that in this case, it is possible to concentrate the energy density, current density to small localities in the dimension hundreds microns. And more detailed investigation of filaments give potential to study small structures with high plasma density and magnetic energy having the connection with submillimeter sources of fast neutrons. Here are a few attempts how to measure magnetic field, direct measurement of magnetic field in PF1000 by Faraday rotation. Now we tested it two campaigns, but without result because in this case we have problems with big mirrors which depolarizate the orientation of the polarization plane. So it is everything, and I like to mention that it is important to study plasma focus Z-pinch because it is the simplest device where it's possible to study the fusion reaction. And it is possible when in maglev type and NIF system, we can observe confinement of the fusion product in hot plasma. We can also use for heating also fast particles, inhomogeneities. It is necessary to concentrate only on the thermonuclear type of fusion. I think it is possible.
Yeah. Thanks, Pavel. Are there any questions? Hans, please.
Yes.
Who's yeah, please.
Some question. Bilbao.
Yeah. Hi.
Yeah. The first question is about the small structures, you know, because you have maybe some diffraction limits in the measurements. I don't know how is the limit, no? Due to diffraction.
Which limit you means?
Diffraction.
Due to diffraction of light in the optical system, I mean. Because this is there should be a smaller limit for that, no? I don't know how much is that limit.
The limit for size is about 40 microns.
40 microns, about that.
Microns, yeah. Yes. It is the diameter of the filaments in a small device. In PF1000, we have this scale in the order 1 millimeter.
Okay. And another question, because I remember, for example, at the plasma focus at Frascati, no, there were similar measurements, no, in the beginning of the 80s or end of this. That the structure of the pinch, I mean, it was dependent on the pressure, no, of the filling pressure of. No, and I remember that, for example, at very low pressure, there was the the current sheet was unstable before arriving to the pinch, for example. No? Then there was at about 3 torrs, there was a regime that was an almost stable column, very, very stable column. I mean, in the Frascati
Yes.
1 megajoule. No? And at very high pressure, there was filaments during the compression stage. There was very, very different dynamics according to the pressure. I don't know which
Yes.
regime you mean in this case, no? The low
Yes.
pressure, high pressure, or
Yes.
that is my
Yes.
question.
Yes, you know George Linhart in Frascati, probably. Yes.
Yes.
It is interesting. You are right, but I show in my picture that similar evolution we observe in laser plasma in density 1, 2 order higher, and in times which is 2, 3 orders lower than in a plasma focus. Yes.
Yeah.
That similar phenomena may have very wide scale.
Yeah.
And similar phenomena we see in solar flares, yes.
Yeah.
Probably in
Okay.
tokamak, the reconnection, acceleration of fast particle instabilities. I think, no, it is necessary future study of this phenomena.
Any other questions?
Because no,
please.
sorry, just a
Yeah.
comment. Yes, because it is not simple to measure the magnetic field inside, no? Because
Yes,
Faraday
yes.
rotation is some integrated measurement along the light, no, along a line. And for example, if you put a magnetic probe, you can also this is you can modify, no,
Yes.
the magnetic structure. It is not
We
simple.
yeah, in our case, in Warsaw, we have density 8 times 10 to 24. We have sufficient magnetic field. The distortion may be 3-4 degree, but the problem of big window decrease the polarization plane. And second problem here can be, I think, in diamagnetism. Maybe that in this slow evolution, we have opposite current to the internal currents, and probably for the necessity of symmetry, we observe formation of the plasmoidal structure, toroidal structure, but magnetic field may be lower. No, it is necessary experiments and it is very
anybody else?
phenomenal.
Any other
Just
question?
a quick question, Pavel.
Yeah.
How many filaments in the PF1000 do you estimate exist at one time within the plasmoid? What's
Yes,
the
Eric.
multiplicity?
It is, yes, we interesting about this. Me seems that the number of filaments is similar as number of cathode rods, but maybe it is 2 times. That here maybe the complicated structure, as mentioned Bostick in these ideas, that filaments are 2 types which reach current in the opposite direction. This, the number is similar to the number of cathode rods. Maybe 2 times.
So it's about 30 filaments?
No, it is 12. 20,
12
about 20 filaments, yes, about 20 filaments.
20 filaments, okay, great. Okay,
But
thanks.
it is axial filaments, the azimuthal filaments, J number may be a few tens, much higher value. You know, in this case, the azimuthal filaments must have only very small current, about 2, 3, 4 kiloamps, and very thin diameter. And structure of the azimuthal and axial filaments was structured. The mesh is different. It isn't seen that they are connected. I don't understand these things. It is very, very complicated.
Any other questions? Anybody else? I have some question and comments for Pavel. Pavel, first of all, congratulations. I think this is excellent work. Yeah. Can you show me slide 16?
Number
16, 16.
15.
16, 16.
Yes.
16.
15?
No, next. Next slide. Yeah. Now if you look at the first part, the figure A, you see a number of spots there. You know, it is not a uniform light. It looks like a very large number of tiny spots.
No, it is anode. Yes.
No, in the umbrella-like shape in the tops.
Yes, it is umbrella shape. Yes.
Yeah, you see the density, the intensity is not uniform. It is made up of small point particles, points. You know, you see that this is. It looks like a very dense network. Is that so?
Yes, but I think it is dimension of the channels. It is registered by multi-channel plane.
Okay.
Yes, and has tubular electrodes. Yes.
Yeah. So okay. So that is actually a part of the detector. It is because of the detector is having that fine structure. Is that so? The detector, the multi-channel plate is causing that structure. Is that so? The MCP.
the MCP detector.
Okay.
Pinhole and MCP. Yes.
Can you show me slide 17? The next slide. 17. Next slide. Can you show the next slide?
17.
Yeah. Now, if you look at D, there is a lot of these, on every fringe, you see there is a lot of something like hair, you know, small hair-like structures are there. What are
No,
those?
we see azimuthal filaments only in the boundary.
No, I'm saying you look at, how do you do annotate? How do you annotate?
No, we interpret as we see these filaments only due to its higher length along the diagnostic beam. Yes.
No, maybe I'm
In
not
the
able to
center,
show.
we see big filaments in this part.
No,
Yes.
you go up, you see the, in D itself, the 1, 2, 3, the fourth fringe from right. The fourth fringe from right. How do you annotate? Annotation?
Anode is here. Yes, it is surface of the anode.
No. If you look at these fringes, above this arrow, in the frame D, above the arrow, just above the arrow. Yeah. Paul, how do you annotate? Paul, can you show me?
It is under view option. Go under view option. Click on view option.
View option. Okay, annotate. Fine. Okay. Now I am looking at this part. Can you see this? Can you see that there are a lot of these hair-like things? What are those?
Mhm. No, it is interesting. It may be rest of axial filaments. Maybe, yeah. But with no, it is difficult to interpret.
Yeah, I think, Paul, that is
Yes.
the reason why your work is very, very important. You see,
Mhm.
this
Yes.
feature cannot be an artifact. It cannot be an artifact. You cannot do this, get this from either a detector or any kind of defect in the optical system. This has to be real.
No, it is irregular. Maybe it is physical origin.
Yeah. So it is very important that we keep in mind that there is a new
Yes.
effect. There's a new effect being reported in Pavel's paper. So this has to be kept in mind. Okay. Okay. Now I think it's time for the next talk. Thank you, Pavel. Can you unshare your screen? But Pavel, very good work.
Yes. So yes, no, nature is very interesting.
Can you please unshare? Pavel, please unshare your screen. Okay. Rajdeep, your paper now.
Okay, I'll share the screen.
Yeah.
Yes, you.
Do you see the screen?
Yes.
Okay.
Yes, yes.
Let me present. All right, so I'm going to present basically our work that was done as part of one of the what we call in NTU as a intuitive research grant work, which basically targets towards the development of applications. So these are special projects that are granted by NTU after very, you can say, multiple rounds of selections. If they see a potential in the proposal where it can be developed. So one of the key criteria for selection of the proposals is these are all proof of concept kind of a proposal. That means you don't have to take the technology all the way up to the TRL level 9 or 8. As long as you are able to start well and reach the TRL level 5 and 6, that is acceptable to that. So in this one, we submitted a proposal, and this is a long time ago. This is all 2018 or something like that. So it's almost 6 years. We on this project, so it was finished in 2020, and but it took 3 years for patent to be granted, and it was granted just very recently. That's the long way, and that's why it was not published anywhere, and we never reported in any conferences. So this is about the developing a slow focus mode plasma focus device for extremely well controlled carbon coating technology. And I'll give you the reference to all that. But before going into that, it's not moving forward. Let me check. Okay, so this is our group. As you all know, I think most of the people know in this audience that who we are. So we are basically at NTU. So 3 of us, myself, Paul, who is also here in the meeting, and Stuart, who somehow could not join us today. We work on this plasma focus device and some other things in our lab. Particularly, I also focus on the low temperature plasmas. So the thing is that this plasma focus work was started in our lab, initially called as the plasma radiation source lab, PRSL. It was established in 1991, almost like 33 years ago, by Professor Lee Sing, when he shifted from Malaysia to Singapore. And after that, Stuart joined in 1994, Paul joined in 1996. I came first time to Singapore in 1997, 98, and then I joined in 2000. So it's almost in existence for more than 30 years, and it started with the plasma focus. And one of the major major project which Prof. Lee took on this device was to develop the application of this device, like what just now Ali was talking about in the beginning. And the big project that Professor Lee Sing had was to develop a plasma focus based repetitive soft X-ray source for soft X-ray lithography. And that is the project under which I went to Singapore for the first time. Of course, my job given to me by Prof. Lee was more on the materials. So we continue to do this X-ray lithography work. We even extended to Paul had a project on EUV lithography. He had a student he trained on, which was later on took up by my student. And we also had some projects from which was funded by Krishnan and NTU on the development of the portable neutron source from plasma focus. And that is where we developed the miniature plasma focus. So we have been working on this plasma focus device development, plasma diagnostics related to the different, the radiations that you get from the plasma. But one of the main thing that we kept all along working on in plasma focus device and other plasma devices that we developed. So we have a laser plasma interaction facility because Paul has, expertise in high power lasers, and he established a laser plasma interaction system even in NIE 1 joule system, I guess it was. Later on, that was converted also for plasma material synthesis, basically for because that's where the funding normally we used to get later on after Prof. Lee left. And recently, we are working on low temperature plasmas as well as atmospheric plasmas, and we have done some very good work in that regard as well. As far as plasma focus research work is considered, it almost, that project that we had about 6 years ago, the one I'm going to talk today. After that, we didn't hit any big project or any sizable project. But recently, last 2 years, or rather last 1 year, we again got 3 projects going on plasma focus. One is very big project, which is led by Stuart Springham, because NTU has embarked upon a fusion science program. And we have Professor Xavier Garbett, a theoretician who works on turbulences, joining and leading the effort in Singapore. But a part of this proposal involves on gamma ray spectroscopy. And this gamma ray spectroscopy will be developed by Stuart, and it will be implemented on the West Tokamak in France. This is basically for the runaway electrons, the thermal, super thermal electrons that are there. But our idea is to test that diagnostics first in Singapore on plasma focus device. That's the work we have just started to work on. So the plasma focus part, diagnostics will still be developed by Stuart. So I will take care of the plasma focus part. And in this regard, I have a request to because we have the whole group over here is the plasma focus group. We have 2 positions. One is totally dedicated to a senior research fellow, basically with quite a decent salary, but probably more background directly in the gamma ray spectroscopy or nuclear physics. The second position, which will be under me, is more related to the plasma focus device, where we will be implementing this. So the person will be doing experiments on plasma focus, not only directly the gamma ray spectroscopy, which will take time to develop, but in the meantime, we will also look into these energetic particles. That means the ions and electrons again. So if you have person who who is keen to join us, have recently done PhD or even have a good experience, we have these 2 positions. One definitely is for plasma focus. So if you have somebody, please do recommend. The position is already open. I can send you the link. The person can apply. And if it comes from your recommendation, definitely we will take the person. So we are looking for that. And under the same project, we also have 2 PhD positions. One will be totally on the gamma ray spectroscopy part. Again, Stuart probably will be looking for a person who will have more on a nuclear physics background. But again, the second PhD position is with me, and that will be for plasma focus, basically doing the same thing, not by the research fellow, or in coordination with research fellow, a PhD student. So that PhD position is also funded from the project. Otherwise, all our PhD students are funded centrally, and those are very competitive. But since we have dedicated fund in the research grant for these PhDs, that means we control that position. So if you have any good master's student recently completed the master's, please do recommend them to us. We have the deadline to apply for the PhD position by 31st January. So we are looking for the PhD positions. So please do recommend some of them to join us on this project. Other than this, I have another ongoing project where we are using plasma focus again for developing coating technology. I won't reveal on that because that will again be going out to be patented work. And we have done some very good progress on that. That has also started about 6 months ago. I have one person working on that. And this will be another coating technology, which is quite popular, and but we want to look for plasma focus based development of that coating. And the third project that we have is to develop the plasma focus. Plasma focus is already well known source of the hard X-rays as well as the neutrons. So I am a co-PI in one of the project where the main PI is a material scientist, and he is developing the perovskite-based scintillator materials. And the idea is to test that whether these scintillating materials can be tested as a dual, radiation diagnostics material or not. That means it should be will be able to respond to both the neutrons as well as the hard X-rays. So that part of that project also, I also have 1 year's money. So if you have, so we have basically three research positions for postdoctoral fellows and two for the PhD position. So please do recommend. So plasma focus, I don't think I need to go into the details of any of this, the things that are there in these slides, but because the focus of this talk is going to be on the materials part, what is most interesting for us from the materials point of view is that once you get this plasma focus, pinch plasma column form, and if you form the pinch plasma column with probably one of the best possible efficiencies, then we all know, as you can see in the shadographs that are taken in our plasma focus, you get these instabilities, the kink and the M0 instabilities, which basically also accelerates the ion to very high energy. So we get this very high energy ions with tens of keV to MeVs. We get a hot plasma jet stream moving in the forward direction. So we get the hot dense decaying plasma. The temperatures are well known about keV range plasmas, and we also get the electron beam which goes in the downward direction, and a lot of ablation of the materials can take place. So that is the ablated material that we use for deposition. If you don't want deposition, we just keep the hollow anode and we can process the material that is placed down the stream. But what we realize with our work on the materials, that it is not necessary that one should always be focusing on the plasma focus in the efficient mode. Normally we call it as a fast focus mode, where you are getting a very efficient pinch, and that efficient pinch is reflected in the form of this big spikes in the voltage probe signals or a big dip in the current probe signal. So this talk today will be about a plasma focus, which is different from this fast focus mode regime. So these are the different plasma focuses that we have at NIE. This is the one on the left is the UNU ICTP device, the famous one developed by Prof. Lee Sings. The second one is just the same version of that, but that was dedicated particularly for the carbon nanotube formation. So it has a inbuilt heaters in between, and it has a cooling which can be done on top of it. And we dedicated it for the deposition of materials, particularly for the carbon nanotubes as well as the graphenes and other things, so some carbon-based product. The one on the third one, NX3, was the dense plasma focus device that we developed as a neutron source with a slightly higher neutron yield of about 10 to the power 9 neutrons that we got from there, about 3 times 10 to the power 9 that we reported from here at about 10 kilojoule operation, not 20 kilojoule, but this can go all the way up to 20 kilojoule. And on the right is the one which we have is what is called as the NX3, not NX3, sorry, LVSFM device, which I will be talking about today. And we have also developed these repetitive plasma focus devices, which can be operated at the repetition rate of 10 hertz. NX2 was the one which was developed by Prof. Lee for the lithography work, and that could be operated at 16 hertz. And that was mostly operated in neon. It was optimized for neon, and we could get the neon yield of about 80 to 100 joules per shot. And the one above it is the FMPF device, which we developed, together with not together, but in collab in a project which was in collaboration with Krishnan. And that is the one from where we could get 10 to the 6 neutron per shot. That means 10 to the 7 neutrons at 10 hertz operation. So these are the different diagnostics we have. So we are pretty okay. We have a large set of diagnostics looking at plasma focus, not only from the electrical signal, magnetic signals, or diagnosis optically. We can measure the hard X-rays, soft X-rays. We have a whole set of diagnostics for the neutrons, which basically are all developed by Stewart, and we also have the optical emission spectroscopy. So many of these diagnostics are not working all the time, and we just bring them when we have projects. So recently, as I mentioned, the projects were either on applications. So most of these diagnostics are probably in the cupboard somewhere. So as far as the material is considered, this is the one you see on the right is the images of fast gated images taken by the 2 nanosecond gated ICCD camera on the UNU ICTP device for a multiple shot sequence where the delay was being adjusted. And what you observe over here, the plasma goes, focuses at the top of the anode, and then it goes and then it accumulates at the material that we place down the stream, which we normally use for processing of the material. And the material processing can lead to the many different effects on the material that is being processed right from the phase transitions to a different phase. You do the surface reconstruction depending on the distance where you are placing your substrate. If you place too close to the anode top, then definitely a lot of energy is deposited on the material. The surface gets melted and can resolidify, totally changing the surface altogether. You can do ion implantation, and we have done several work on ion implantation, implanting different gaseous ion into the materials and thereby changing the properties of the materials. We have done the nanostructurization of the materials, again because of that features comes into the picture when you are at certain distance. If you come too close or go too far, then you don't achieve that. And we also have converted the nanostructures on the thin films, not necessarily of the solid target, but you deposit the thin films, expose them to the plasma focus, and we have formed very nice nanoparticles of very uniform size distribution for our FEPT, COPT work, because we did a dedicated work on the magnetic materials. And we have also grown even the one-dimensional nanostructures on the polyaniline thin film. So all these works are all well published in different work. As far as the depositions are concerned, most of the depositions that we did was by using a solid anode, mostly in the form of metals, and then filling the background reactive gas, which can be nitrogen, carbon, oxygen, or mixture of this, or other devices, other gases like acetylene, methanes, and so on and so forth. So you can coat any kind of material that you are interested in using the plasma focus device. And what we have noticed that we normally get superior or enhanced properties of the material, and you can all understand that very well, because as I mentioned that you get these high energy ions in the plasma focus, and most of these depositions are not single shot deposition, these are multiple shot deposition. So as you can guess that when you are doing a deposition, first of all the energetic ions of the filling gases species goes and they hit the target. So in a way they process the target surface, remove the oxide layers if there are any, or even sort of do a kind of a plasma cleaning over there. And then ablated plasma reaches over there of the material of the metal that you have placed at the top of the anode, and that gets deposited. And the next shot when you fire, again your ion, the species of the energetic ions goes up there, process it and deposit it. So in a multiple shot deposition, you are doing deposition plus processing, both of them together. And that in situ processing, we have done the calculation of the temperatures by solving the equations, suitable equations, and calculated the temperature. They can exceed beyond the melting temperatures depending on the distance. So it is basically very high transient annealing, very high temperature transient annealing, which is not available even in the normal thermal annealing experiment. And the good thing is that here the annealing is done in the microsecond time scale. So you're not doing it for 1 hour, 10 hour, or 15 hours like what material people do. And we can grow any kinds of nanostructures. We can grow nanoparticles. We can grow nanoflakes. We even have grown nanotubes. And this is basically one of the pictures that was taken by one of the students, final year students, BSc students, recording the ablation of the anode top material. In this case, it was a graphite. And graphite materials, and you can imagine the figure A is basically just very close to the, just after the pinch phase, where the ionization bubble has already formed moving forward. That means this is just after the pinch. And I think the time is mentioned, it is 41 nanosecond after the voltage probe peak signal. And you can see the ablation is starting to take place. And we have noted that the ablation lasts for about a few microseconds. In fact, in some cases, we found that this materials ablation can continue all the way up to few tens of microseconds also. So a lot of work has been done by our group on this in this thing. The first work in this case was done in 1988 by I think this group is from Argentina, by J.N. Figes and Atwell. They processed the stainless steel and titanium also using the nitrogen plasma. And the next work was my PhD work, where we processed the thin films of PZT, lead zirconate titanate, using this device. And then there are a whole series of work that has been done on this in this plasma focus device by our group. So we have published more than 90 papers on the materials related work on the plasma focus itself. And we can do any kind of depositions. We have mastered the technique. We have mastered the device. We have operated it in the different zones. We can do the depositions purely gas phase, where the anode material is not being ablated at all. So that means we have gone from the basically from the ablation of the anode top material to a pure PECVD kind of a system, where you are just using a gaseous precursor to deposit the material. Like in the second image, you see one-dimensional carbon nanotube, one of the highest growth rate of the carbon nanotube that we have reported. So this is also the work which we wanted to patent. Of course, we couldn't patent it. We have not yet published it. We can grow very uniform two-dimensional films. We can grow three-dimensional graphene flakes as well using these things. So we can coat metal by bimetals, trimetals. We have recently even coated which we reported in the recent ICPSA conference, high entropy alloy. That means 5 and 6 elements together, and that too in a high entropy phase. That means a single phase with the appropriate entropy being involved in those materials. So, so what we have basically found that plasma focus offers a very unique kind of opportunity, because in the material science, all the devices, they are the low temperature plasma devices, basically low temperature plasma. There are some thermal plasma deposition schemes for the material or the processing of the materials, but the temperature is still within the order of tens of EVs, or maybe not more than 20 EV. And the density of plasma over here is much higher compared to those low temperature plasma. So this is basically a high energy density plasma device system, where the material ablation from the anode top is very high. Even if you use a gas phase, we typically can achieve very high deposition rates because it's a multiple shot deposition, and the film is being processed in the next shot. So most of the time, these impinging ions, they act like hammer on the film, and they deposit a very dense film, which is normally not obtained by any other method. It's a transient method. It is ultra fast. So you are doing basically some millisecond deposition, maybe microsecond depositions. You can achieve in situ phase transitions. We normally get materials with the superior material property, and with the enough experience, we can operate it in many different ways to grow any kind of material that we want. With that as general introduction to this, let me go to this work that we did with reference to this. And this was for the carbon overcoat, and carbon overcoat for the for the magnetic hard disk. So we know nowadays, whenever you buy the computers or the laptops or the desktop you're buying now, they are coming with the SSD hard disk, and you may be thinking that everything is now going into the solid state technology. That's true, but bulk of it is still using the magnetic hard disk storage. Okay, because the cloud storage is all still magnetic, and magnetic materials, they normally have this disk platter, and where you have a magnetic material, but all these magnetic materials are protected by a hard coating. And the technology, because they want to have what is called as the higher and higher packing density, and in order to achieve the higher and higher packing density, they are also coming out with more different technologies. when this project was written, heat-assisted magnetic recording was in limelight, and it was predicted that it will come into the market in another 2 to 3 years, like that means by 2020. Of course, it took time. I think HAMR came into the market this year. And what it utilizes the laser beam to be focused on the magnetic materials to write the data bit. So to change the phase of the materials to write in the form of the zeros and the ones. And therefore, the change in the magnetic materials phase using the heat of the laser required the carbon coating at the top to be very thin, and also, something which is not modified by the treatment during this heat treatment. And the current technologies that were available at that time when we were doing this project were so what was the main requirement for these kind of thin film was that they needed to be, let me just go directly into this and not so what was the requirement is that they had to achieve two things. First of all, the coating of the carbon, which is there at the top of the magnetic materials, need to be reduced from about 2 nanometer to less than 1 nanometer. That was the requirement. And second thing was that the sp3, that means the diamond-like content of this carbon coating must be greater than 30% in order for them to survive under this HAMR, environment. So these two requirements. Also, you have to have the coating uniform over 65 millimeter platter of the magnetic hard disk. So the coating technologies that were available at that time, none of them were able to provide the high sp3 content coating. The typical coating that are used by industries are the basically PECVD based and filtered cathodic vacuum arc, that technology developed by the nanofilm company from NTU Singapore itself, and the magnetron sputtering. So we believe that our proposal was based on the fact that there is a new alternative technology that is needed, and we propose that plasma focus can do that job. So let me just, and this was based on our hypothesis was based on our preliminary work. We deposited some coating using our conventional plasma focus, the fast focus, most plasma focus. We were able to get thin films, not too thin films, but about 5 to 6 nanometers. But what we were motivated by was from the fact that our sp3 content was about 74%. So we thought that, okay, if we can get 74% with just some normal hit and trial method, if we can do some controlled experiments, then probably we can get the coating. But the big problem was with this UNU ICTP device, that we cannot get a coating with the uniformity more than 1 centimeter by 1 centimeter. And the target for us was to coat on the 65 mm coating. And this project was supported not technologically, but morally, with the letter of support by this Showa Denko. Showa Denko is one of the very big company in the field of this magnetic hard disk. So Showa Denko, Seagate, these are the top companies in this field, and they were interested to give us their samples. That means give us their platters without the carbon coating. They were willing to do the validation of the results that we are getting to confirm what we are saying or what we are promising, are we getting or not. So that was done by them. So we did this project in stages. So first of all, we changed our the plasma focus to this fast focus plasma focus, which is a small volume fast focus mode plasma focus. We changed it to the mid volume. That means we increased the anode radius. We operated the device at the high pressure. And that was basically done to achieve the coating of the bigger dimensions and basically to see whether we can get about 30 mm coating with the sp3 content greater than that. And this was basically to buy out the time which we needed to develop the LVSFM device. And we demonstrated that. So I'm not going to present the results of this MVSFM, which was basically a UNU ICTP device, just with the anode modified to a bigger dimensions, and accordingly the operational parameters were changed. Then later on, we developed this device called LVSFM, which stands for the large volume slow focus mode DPF. For this, we developed the device altogether from the beginning. And the whole idea was to have an electrode with a much bigger dimensions, where the pinch plasma is first of all not very, in the fast focus mode, it pinches gently, doesn't need to be very efficient. That means no need to be the current being very high, even if it has a large inductance. It must be, in order to achieve the larger anode dimension for a moderately sized plasma focus device, what we did was we have to either increase the capacitance or the inductance. So we increased both of them compared to the UNU ICDMP device. We went for a 6 times bigger capacitance, about 180 microfarad, and we also increased the inductance of this device. So our NX2 device is just 26 nanohenry, inductance, very well made device. But our UNU ICDMP is just using the cable, so that has a larger inductance of 110. In our LV-SFM, we deliberately increased the inductance to almost like 500 nanohenry. Also, all that was done in order to change the quarter time period of this device so that we can work with the larger dimensions of the plasmas, so that we can get the larger or the bigger coating in our system. And also we can keep the pinch plasma away from the wall as much as possible. So because larger quarter time period allowed us to go for the larger diameter of the anode as well as the larger length. So this is just a conventional UNU ICDMP device. Everybody knows about that. So this is the typical dimensions. This is the plasma focus large volume SVFM device that we developed. So this, as you can see over here, the last column, the inductance was almost close to 500 nanohenry. It was using a capacitor, as I mentioned, 6 times bigger than the capacitors of the UNU ICDMP device. And it look at the anode radius, it is 80 mm, almost like a 10 cm. And it was very long anode. It was almost like 50 centimeter, 47 centimeter long anode. And you will see the picture in the next one. Oops, sorry. So as you see over here, this is the capacitor bank of this device. Actually, there were 2 capacitors of 175 microfarad, but we used only one. So in principle, this device can go to 20 kilojoule, but we again operated at half the kilojoule because one capacitor was good enough for our work. We did not want to make it. And look at this, the chamber on the right. This is just before the assembly because you don't see the cables connected over there. And that's the lower chamber. And a quite bigger diameter. And the quarter time period of this device was, I think, more than 12 microseconds or something like that. And we deliberately added, you see, two coils, these blue color coils that you see over here, to increase the inductance of this device. Otherwise, the inductance was also quite, the guy who designed this who fabricated this for us, initially was with the rail gaps, with the low inductance and directly connected. So later on, we disconnected that and put these 2 coils, 2 singleton coils to increase the inductance. And we could get the focusing over here, typically around about 12 to 13 microfarad, but with a suitable gas pressure and further adjustment, the focus, very thick focus, was achieved at about 20 microseconds. And it was verified using the gated ICCD imaging that the pinch is still forming. It's just that on the voltage probe and the current probe signals, you see very weak indication of pinch. And that was deliberately done because, we need to understand this. This coating needed to be done on a magnetic material. If we operate our plasma focus in the fast focus mode, then the ions that are going to come out, if they are the ions of the filling gas, and in this case, we are going to have one of the precursors, the carbon gas. If the carbon plasma is too energetic, it is going to modify even the magnetic layer. And we did not want that. We did not want the magnetic layer to change its magnetic properties. And we all know that the plasma focus is known for very intense plasma jet and very high energy ions. So the idea was to minimize those possibilities of changing the characteristics of the material that is already there. We were doing it on the magnetic materials, which were provided by Shobha Denko. So we did, so after these slides are all material science related, maybe not that much of interest for you, but let me assure you by going through these that we achieved what was promised. So with the multiple shot deposition, we were able to show that, okay, if you go for just pure methane, the films were getting very thick. So we continued to do the dilution of methane in the nitrogen, and for the 90% neon, 10% methane, we were getting 1.2 nanometer film thickness per shot for the deposition distance of about 50 centimeter. And this larger deposition distance was achieved by putting an extra chamber, the extension chamber, which was added to it. Otherwise, at the closer distance, films were too thick. And our aim was to get the film thickness less than 1 nanometer. And we further changed so we changed this different combination of the gas, dilution ratios. So neon 95%, methane 5% gave us less than 1 nanometer per shot, and that is what we used ultimately in our depositions. We checked the quality of the film. They were highly uniform without any dust particles on top of them. The roughness, average roughness, was within the range which was demanded by the Showa Denko company. All these samples, after being tested and measured by us, were sent to Showa Denko, and they will give us the feedback what kind of samples we are getting, whether they are satisfied with them or not. And so they were all passed their validation tests. Then we did basically angle resolved XPS. XPS stands for X-ray photoelectron spectroscopy. And this is basically to find out what materials we have at the top of the surface. Because we were seeing that the carbon coating is about is not 1 nanometer as we expected. It was coming out to be 2 to 3 nanometer. But later on, we realized that these coatings, by exposure to the atmosphere, were already getting this, what is called as the adventitious carbon. And there is a way to characterize this, because the nature of adventitious carbon is different from the high sp3 content carbon overcoat. And that resolution was done by doing the XPS at the different angle of 10, 25, 50 degree. And by that, we were able to estimate, with the help of some material science expert in A-STAR, the group that we have in Singapore, that the adventitious carbon layer was about 1.7 to 1.8 to 2 nanometer. And the carbon coat, the high sp3 coating, was below that. And the estimates of the sp3 content, we got remarkably excellent results, with the sp3 content going higher than actually 70% as you can see over here for the different materials. And these were all done on the disc platter, that means 65 mm. And these percentages were verified not only by the XPS, but by other diagnostics, other characterization methods, like electron energy loss spectroscopy. We also did in order to see how uniform the films are, we do the what is called as the optical surface analysis of the this is a standard industrial method by which they look at this film, how uniform the coating is. The one in this right, the boxed film is the commercial carbon disc. Initially, I mean, if you don't handle the disc properly, because we do not have the clean room environment like the industry had. So if we don't handle it properly, the film becomes like what you see over here, no deposition. We did not do any deposition, but handling itself makes the film dirty. So initial depositions were not very uniform, like what you see on the film on the left. But after several experimental iteration, even without putting a magnetic filter, limited magnetic filter to low energy, without that, at a larger deposition distance of 50 centimeter, after very systematic, procedural changes, we were able to get a very uniform film, almost as close as to the commercial carbon deposition films. These coatings were uniform within 20%. But another big thing that we wanted to verify was that the magnetic properties of the underneath film should not be changed, and that is what we demonstrated. Even after the 10th shot, remember it, the coating was done within one shot. And so we even fired 10 shots. Look at the curves of the magnetic characterization curves before being exposed and after being exposed. They are almost identical. And the coercivity did not change significantly. The problem, the main thing is that these are the materials which are going to store the information in the magnetization. Basically, the coercivity needs to be very high. All these materials which are used for the magnetic recording, they are hard magnetic material. Their coercivity has to be greater than, hard magnetic is anything above 100 Oersted, the coercivity value, the HC value. But normally they are much more than thousands or even few thousands. So you see, after even plasma focus exposure in the slow focus mode, the coercivity was intact. It did not change. And it was confirmed for multiple sample. As you can see over here, the coercivity remained very high of the underneath sample. So sample's property, that means the underneath magnetic layer, was totally intact after this. So the conclusion was that we developed this alternative plasma focus based technology for carbon overcoat. This is the patent that is listed over here. We successfully deposited the film with the thickness within the range of about 0.9 to 1.2 nanometer. The target was the nanometer. We achieved it. The target for sp3 content was greater than 30%. We actually achieved greater than 70%. And we successfully achieved a large area coating, that means on 65 platter. And with the coating uniformity for 1 nanometer film was 20%. That means 0.2 nanometer, the coating variation thickness. And that was, I think, was not, we were not able to prove that, but we felt that it was just the disc platter itself had that kind of a profile, and our coating was just following that profile. And all this done is within a single shot of the plasma focus device, a sub-second deposition. Industry, the Showa Denko, their deposition process, each disc, the entire process, the carbon coating part is 6-second availability. There is a 6-second window that they have reserved for the carbon coating for high volume production. We were able to do that. Imagine if you develop this plasma focus device with even 1 Hertz repetition rate, we are done. We are good. And because you have 6 seconds, so we can do it within 1 second. And in fact, we can do even higher, faster than that, but they don't really need that because there is a certain feedback rate coming from there. So yeah, so this is where I stop. Yeah, thank you.
Yeah. Rajiv, congratulations and excellent work. But I think we should move to the next talk now. Can you
No questions? Why no questions?
Yeah, if you want, slightly we are running behind
let
time.
Them ask, why are you not giving them the chance to ask?
No. Sure. Yeah, okay, we'll have questions.
Because I think the first talk was delayed by 10-15 minutes. It's not that my talk is
Sure. Okay, sorry.
I think
so any questions?
Yeah. If there are any questions, just ask. If no question, fine, then we move forward.
Yeah. Any questions?
Good evening. Can you hear me?
Yes.
Hi, Prof. Rashdeep. I'm Lim here. Very interesting work on your material processing. I would like to ask for the slow focus mode there. Is the pinch still intended in a slow focus mode?
Yes, the pinch is still intended. We still see the pinch being formed. You see it in the voltage probe signal, a very small hump in the which we normally get. And the second thing is that we did also what you call as the optical imaging, and you can see the compression. You can see the compression going at the top.
I see. So the slow focus mode refers to the pinch is delayed to be quite later time, or the speed of the current sheet rundown is being slow.
If you read our plasma, if you read our this patent over there, we define the slow focus mode, a particular mode where the actual velocity of the plasma is less than 1 centimeter per microsecond. So we said that if the plasma focus is running too fast in the actual phase, it will always most probably enter into the fast focus mode. So in order to get these slow pinches, the analysis is provided in that, if I remember correctly, in the patent, that the certain characteristics that the plasma focus need to have in order to call a slow focus mode, and that is we defined it with respect to the dry factor, with respect to the velocities, and relatively weak pinch. Yeah.
Okay. One last question is that I saw your cathode is longer than the anode. Is that purposely to do so?
Okay. I think that is not an issue. I mean, it can be bigger or shorter, or even if you don't have a cathode, plasma focus, it still works. That is what our experience is. So cathode is not that important, but we normally find that if you have a parallel running a perforated cathode, like in the form of the rods, then it works better. It's better, but it will work in any situation. Yeah. Anyhow.
See. Okay. Thank you for the explanation. Thank you, Prof. Rashid.
Any other questions? Well, I have a question. You define the slow focus in terms of the velocity. So if you add a higher instead of neon, suppose you had used argon, suppose you had used krypton or xenon, it would have been still slower. Would that be?
Yeah. So I think in that case, what we try to say, probably I don't remember, because this patent itself was written 3 years earlier, and we did not write a research paper on that. So it was basically because the patent examiners were asking us, how do you differentiate between the slow focus and the fast focus mode. So we looked at all our results and all that, and we realized that when we have this slow focus mode, the so-called very weak pinching, and to get this kind of dimension, our speed was always less than 1 centimeter per microsecond. And our experience from the Lee model code for the UNU ICDMP devices, that for the typical speed for the plasma focus to work very efficiently, where you do not need, which is probably neutron optimized, not maybe the pinch optimized, but neutron optimized, is 4 to 6 centimeter per microsecond in the actual phase. 4 to 6 centimeters. So we are far below that.
Okay. Any other questions? Yeah. So, do you have plans to actually make a quasi-industrial prototype?
Yeah, so we actually applied for a very big research funding based on these outcomes because the results were very good. But sometimes the change in the leadership, the CTO of the Showa Denko changed, the one who was working with us. So they were willing to incorporate our device in their assembly line if we can develop a repetitive plasma focus, because they cannot test a single shot focus for us.
Yeah. Okay.
So we submitted a proposal about $6 million to Singapore, what is called as the Central Gap Fund, to come to develop a plasma focus which can do coating on two sides of the platter simultaneously with two plasma focus from the opposite side. Unfortunately, the project was not funded. Probably we did not have a very strong supporting letter from this, even though they say that okay, they will work with us, but yeah. We did not get the funding, so it did not go further. But if there is any industrial taker, definitely we would like to work with on it. It has a great potential.
Yeah. Okay. So thanks, Rajdeep. Now, is Eric around? Eric?
Right here.
Yeah. So can you start presenting, please?
Okay, let's see. Just a second. It got lost. Hang on.
¿Se ayuda? Sta arrivando Lerner.
Yeah, I'm having some difficulty. Sorry. I don't understand why it's not showing up.
Yeah. Yeah, we can see it now.
What?
No, well, it just went.
All right. Let's try again. Finally. Okay. It's not letting me go to the
Yeah.
full screen.
Yeah.
But people can see this now?
Yeah. You can.
Yeah. Yes.
Okay.
You can use this to make your.
What's in them?
Yeah. You can try to put a full screen there and presentation mode here.
Okay, finally, I think I can get it. Finally. Okay, so we're talking about our preparations for moving to operation not with deuterium, but with hydrogen boron. We haven't quite reached there, but we're making progress despite the problems. So what do we expect? Well, the best results we've achieved with deuterium are 250 keV with an n-tau of 10 to the 12th and 2.5 times 10 to the 11th neutrons. If we could replicate these conditions with PB11, we'd expect about 2 trillion PB11 reactions. So about 3.5 joules of output for 60 kilojoules input. Our ultimate goal of demonstrating this as a practical fusion device is to get to 600 keV, which would give us more than 60 kilojoules output. So that's where we hope to be going. So what we're planning to do is to use decaborane, which is H14B10, as the PB11 fuel. It's a solid powder. It has to be heated to 40 to 70 C to get enough vapor pressure. Now, it is toxic, but it's easily converted to boric acid by bubbling through water. And we've attached and tested this little bubbler, which we've put on the exhaust. So we know we're ready to exhaust to the atmosphere, a safe combination of gases, which is just going to be pure hydrogen. Okay, go. Oh, right. This is the bubbler. So in addition, we have to modify the setup in various ways.
Eric, we are not able to see your further slides. We are only seeing your title slide. It is not moving.
You could have told me that.
Yeah.
All right. Okay, can you see this now?
Yeah.
All right, we'll just go in this mode.
Fine.
So, yeah, all we missed was this was the bubbler that I was illustrating. So we've had to make some modifications to the machine to accommodate the need for heating it continuously while it's on. So we have this upper vacuum chamber for the E-beam. So we had to install heating tape and insulation on top of it so that it could be totally electrically isolated. Because when the machine operates, this top plate, of course, goes to 40 kilovolts. So we installed remote operation so we could entirely disconnect the heating right before the shot, and it would have no path to ground. So in addition, we're trying to make preparations for a decaborane distribution system. Now, the decaborane we're using is ultra-high purity, ultra-high isotopic purity, but it's only 100 grams. So we're keeping it in a very small vessel, but we're going to attach it to a larger mixing vessel, which we're still in the final stages of preparing. So the second part of our preparations, and the main part that I'm going to focus on, is preparing the conditions for operation that we think will lead to successful observation of PB11 reactions. So over the last 3 years, people are probably aware from my previous presentations, we've been upgrading to a dual switch per capacitor to increase the current and reduce the induction. And after 3 years of working on the switches, as well as getting other results, we completed this task in May, and the switches now are simultaneous to within 10 nanoseconds and are pulsing reliably. So what happened was, back in May, we demonstrated that the inductance drops from 26 to 21 nanohenries. The resistance also drops of the entire device from 8 to 5 milliohms. And we get a big increase in peak current. So this is the record pulse we got back in 2016 with the old pulses. And this is what we got in May. Since we increased the current, we had to increase the pressure up to 40 torr, which I'll get to in a minute. So this is what we did in May. But with 40 torr, we found that there was poor compression and a slow pinch. In other words, the dip, the DIDT was only about 7 or 8 teraamps per second, kiloamps per nanosecond, instead of our record was about 17. And we found we were still getting a slow asymmetrical breakdown at high pressure. Naturally, the higher the pressure, the more difficult the breakdown, and therefore, other things being equal, the slower. So in this picture of the sheath, which is heading in this direction down and to the right, we see that there's sort of a pre-breakdown in front, which is very irregular, before the main breakdown and the formation of the filaments. So when we tested with trigger shots, just using the trigger as the source so that we could observe from the bottom safely, we saw the same irregular breakdown. This is the breakdown at 22 torr, fairly regular, and at 40 torr, it's quite irregular. And we know that other people, the USCD device at only 1/4 megaamp, they also found as they went to higher pressure, in their case from 2 torr to 6.5 torr, they got very irregular breakdown. And Lawrence Livermore, which got up to 3 megamps, they encountered this problem at a lower pressure than ours at 20 torr. So what we did during the summer, we experimented with various approaches, and we found 2 things. One is that we were incorrectly mixing the gases. So we were mixing in nitrogen, small amount of nitrogen, with the deuterium. And we were actually getting inadequate mixing within the vacuum chamber. So by simply changing our mixing approach, we got an even mix of the deuterium and the nitrogen. In addition, we turned on the low current pre-ionization. This is tens of microamps, and we were able to get a better breakdown. So this was the shot back in May, and now in October, we achieved even higher peak current. This is 1.8 megamps. So almost a 50% increase over what we were getting with the old switches. And that gives us a record I² over energy for any DPF, which is, we measured 27 over the 27 over microamps microhenries. So the overall inductance at the pinch was 37 nanohenries, which, as far as we know, is smaller than any other DPF. And we were able to get back to a very rapid pinch. So in October, we were up to something like 13 kiloamps per nanosecond. So all of that led to an improvement in fusion yield. So our fusion yield tripled to 6 times 10 to the 10th. But that's still not good because it's only a quarter of the record that we got way back in 2016. And the ion temperature we measured by time of flight to be 33 keV, which is, again, too low for what we are expecting with what we're needing with the PB11, which is about 150 keV. So we looked at what was happening to the filaments, and there were interesting changes in the filaments. Again, this is about 700 nanoseconds into the rundown. So back in 2019, we were getting thin filaments, but we were getting them very disorganized at the front of the sheath. So the filament radius was down around 120 microns, but they were totally disorganized in front of the sheath, and that led to poor pinches. Well, in this shot just 2 months ago, you can see that the alignment of the filaments with each other extends right to the front of the pinch. We don't get a lot of disorganization. There's a little disorganization, but not much. But the filaments are now much fatter, 300 microns. We attribute that to the slow breakdown. Now, we were working on a number of ways to mitigate this at high pressure. One alternative is going to much higher pre-ionization currents. Instead of microamps, we were going to amps in the anomalous glow discharge regime. Now, we tested that again with the trigger, and you can see going from without the pre-ionization on the left to the pre-ionization in this glow discharge regime, we get a very even breakdown. We haven't been able to test that yet on the main machine because we're still working on protecting the circuit against the 40 kilovolts that it has to resist. What? So now we're a little puzzled by the new results with the pre-ionization, because if we use Lee simulation modeling to modeling these pulses, we need to drastically decrease the resistance. But we also have to change the other parameters to get a slower rundown velocity. So in both cases, the alphane velocity is around 12 centimeters per microsecond. But with if we model this pulse with the parameters that we optimized through the Lee simulation back on 2016 with 10 milliohms, then we get much lower current than we actually got. If we get a good modeling of the current we actually got, which is 1.8 megaamps, then we get a lower rundown speed. So what's happening? Why is the energy, some of the energy being dissipated? Well, one of the things that we have to consider theoretically is the critical ionization velocity limit for anything other than deuterium or hydrogen. If you have multiple electrons, you have the problem that the inner electrons are more tightly bound. So for example, with nitrogen, which is our mixing gas, the 5th electron can be ionized with only 98 electron volts, but the 6th electron takes 520. So that's CIV velocity of 8.2 centimeters per microsecond. As Alfvén demonstrated decades ago, if you exceed this, you start necessarily ripping off those inner electrons. So that's going to be even more of a problem with boron because its critical ionization velocity for the 4th electron is only 6.5 centimeters per microsecond. So basically what we see is probably happening is that as the sheath exceeds 8.2 centimeters per microsecond, we started to get this ionization and emission of the soft X-rays. So that's what was probably slowing the sheath down. So that's a consideration that we have to have in planning the conditions for running with boron. A second consideration we realized came from our 2017 calculations of the effects of high Z impurities. Basically, there's a very simple consideration that for filament formation, hydrodynamic dissipation has to exceed ohmic dissipation. Because if you have ohmic dissipation dominant, the current wants to spread out. When hydrodynamic dissipation is dominant, then the current wants to form filaments to minimize that dissipation. So that depends, basically, we found out working through these numbers, the fraction of the high Z material, or higher Z, these are all low Z mixing gases, is a function of this formula. And the number of filaments enters in, because the smaller the number of filaments, the more powerful each current is, and the easier it is to maintain the filaments. So that means we have a maximum number of filaments in the machine for a given mix. And what this table shows is we calculated for small mixes, we can have more than 100 filaments, which is observationally what we have in our machine. But for heavy mixes, which we'll need to get up to run with pure decaborane, the number of filaments goes down. Now, we have 32 teeth and 16 veins in our cathode. So you would expect, as Pavel says, twice as many, 64 filaments, but we actually observe over 100 filaments. We think we know why, and we think we know we have to reprofile these teeth so as to reduce the number of filaments so that we can get up to the heavier mixes. So that's where we were in November, and we were about to see whether we could improve the functioning of the device sooner by increasing the axial field with our axial field coils. But unfortunately, experimental difficulties intervened, and this is something that we just discovered, but instead of breaking records, we broke an anode, breaking news. So the anode cracked. This is a beryllium anode. And we see from where it cracked, which was deep inside the hole inside the anode, it was due to the erosion from the E-beam halo after about 300 shots. Now that's better than our first beryllium anode lasted only 100 shots. And we're pretty sure that we know the redesign. We have to make the hole inside the anode larger to get away from this halo around, the conical halo around the E-beam. The problem is the anode replacements will take about 3 months, plus this possible modification of the cathode teeth. So my colleague Syed Hassan said, well, while we're waiting, why don't we go back and see whether we can do experiments with the tungsten electrodes. Now, we moved from tungsten to beryllium because tungsten has heavy IZ impurities. But we figured that during a short run, we can reduce the impurities by initially polishing the tungsten electrodes, getting them very smooth. We observed that the impurities increased fairly rapidly as we ran with tungsten back in 2016. So the goals of this short run that we're going to do, hopefully in February, while we're waiting for the new anodes to come back, is to separate the changes we've seen in functioning with the new switches from any changes from the decreased impurity. And since we have functional 14 centimeter and 10 centimeter anodes, we'll be able to do a clear comparison of the length of the anodes. So these are some of the questions that we're going to try and answer in this next run with tungsten. First of all, does this low resistance regime that we've just observed require high pressure? Because with a 14 centimeter anode, we should be able to run with lower pressure and get the timing right. Does the low resistance regime need low impurity? Does it even exist when we run with the tungsten? Can this low resistance regime increase the fusion yield if we have good breakdown? Now, the Lee simulation indicates that if the high resistance mode, which is the mode we had with the last tungsten runs, together with reduction in inductance in the switches, will make the sheath run too fast with the 14 centimeter anode. In other words, we'll have a higher than optimal rundown velocity if we get the timing right. If, on the other hand, we maintain the low resistance mode, we might actually get record yields for pure deuterium with a 14 centimeter anode. And we could test whether the heavier mixes run correctly with the 10 centimeter anode. So that's what we're doing to prepare for the operating conditions. Finally, I want to say that we're also preparing for the PB11 diagnostics. Now, PB11 is going to create a problem for us because we expect pretty heavy deposition of boron on the windows. After the pinch happens during the shot, we expect the decaborane to disassociate into hydrogen, lighter decaboranes, and boron. So one question is, can we remove the boron with fluoride gas? The Chinese have done some research on that, and we might be able to do that. But the other thing we're preparing to do is to try and use an X-ray pinhole as the imaging device with an ICCD. Now, second of all, the big problem is we don't produce neutrons with the main reaction. Now, that's a huge advantage for PB11 for producing energy, but it's a disadvantage for diagnostics. If we want the diagnostics outside of the device, we have to use the secondary reaction to get the neutrons. So one of these secondary reactions, which occurs at the high energy tail, is to produce radioactive carbon. Now that's a pain in the neck because we have to remotely operate because radioactive carbon is highly radioactive. But with a 20-minute half-life, it will decay overnight back to background. Now with our existing gamma ray detectors, we should be able to detect as few as 3 times 10 to the 6 nuclei. But we're also acquiring a gamma ray spectrometer, which should have a higher sensitivity. Now, if we use the carbon-11 ratio to determine how many PB11 reactions we've got, that depends steeply on the temperature we achieve. So at 250 keV, we could detect 1.5 times 10 to the 13 reactions. But at 300 keV, we can detect 100 times fewer reactions. That will be the minimum detection. So there is another mode for detecting these secondary neutrons, which is the direct detection of the alpha particles that are produced by the PB11 reaction, reacting again as they slow down with the boron 11. So that also produces ordinary nitrogen and a neutron. The combination of the PMT measurements and the radioactivity can combine to give both the ion temperature and the fusion, ultimate fusion yield, while the X-ray signals gives the length of the pulse. So to give an example, this is calculated. If we get up as high as 1 MeV, and I'm using this high temperature because it just makes the graph easier to distinguish, we will be able to easily distinguish the time of flight of the carbon-11 neutrons, which are going to have this low energy bump arriving long after the main pulse, from the neutrons, what we call the slowdown neutrons, from the alpha particles reacting with the background boron 11, which is going to have this fairly sharp peak at about a delay of about 600 nanoseconds. So that's what we expect to do once we get the boron going. So basically our plan is to do the tungsten experiments in February, to hopefully go back to the main experiments with the new beryllium anodes in March or April, and then to transition very rapidly in April and May to our next big step, which is experimenting with hydrogen boron mixes. So that's what I had to say. Thank you very much, and I'll take questions.
Questions? Any questions? Questions? Well, Eric, I have a question. Have you considered coating your anode with titanium metal? Because titanium would act as a kind of gator for hydrogen or deuterium or proton. So when the impurity which it will emit will be preferentially the adsorbed hydrogen, not the metal. Have you considered such things?
You're talking about coating the tungsten electrodes with titanium.
Yeah.
Well, as I say, our basic solution to the impurity problem is going to beryllium, where we have achieved what we believe to be the highest purity of any fusion experiment in the world. We're using the tungsten just because we're sort of delayed with getting back to the beryllium. So we don't really intend to use the tungsten in the long term going forward. So that's why we wouldn't bother with trying to coat it with other materials.
Yeah. Ali, you have a question?
Yeah, because I work with titanium a lot. We use it as a getter, as you said, a replenisher inside the neutron generators where we store deuterium and tritium in a very tiny titanium element. And the problem here is, yes, the atomic ratio for metal hydride, which is how many how many atoms of hydrogen deuterium you can store into the crystalline structure of titanium, is almost to 1.85, something like this. So 2 atoms of hydrogen isotopes per atom of titanium. The problem is you can degas those very easily after a temperature of 200 degree or under high vacuum and also ion bombardment. You can start to degas them again. So you need instead of coating the the anode, which is prone to ion bombardment, and this will lead to degassing, maybe he can put a getter inside the main body of the chamber, and then this getter can be connected to electric circuit, where if you want to degas everything during the pump down of the chamber, they heat it up, they degas everything, and then they can keep it at a certain temperature while they are operating, so that they can suck all the hydrogen / deuterium impurities from the experiment to this getter, and it will store it. It can store a very large amount of deuterium and tritium inside the titanium if it is clean, surface clean, pristine titanium. This is just a comment regarding using the titanium as a getter inside the. So
Right, but I mean,
instead of coating.
we're actually, I mean, when we run with hydrogen boron, hydrogen is going to be part of the fuel. So we're not concerned with hydrogen. With the tungsten electrodes, the source of the impurity was the electrodes themselves. The electrodes were, we were unable to completely remove the tungsten oxide from the surface of the tungsten. And the tungsten oxide was continuously breaking down during the shot. So you were getting the very heavy tungsten impurities into the plasma. So we expect that that will be a problem again. But as I say, our basic solution was to move away from the tungsten to the beryllium electrode. And we're going to go back to those once we get the new electrodes made.
Any other questions?
Yeah. Hi, Dr. Eric. Thanks for the sharing for the proton boron approach. Just now you mentioned something on the filaments. There's a maximum, there's a limitations of filaments. So I just want to know the idea of the filaments here is if too much, what is the considerations or the effect which might cause deteriorate the performance of the pinch, is it? So sorry, can you hear me?
You several times were breaking up, so I think, could you repeat
sorry.
the question briefly?
Yeah, sure. Because just now you mentioned something about the number of filaments. So there's some maximum numbers of filaments, if I'm not mistaken. So,
right. The problem is,
I just what's the idea of the filaments here? Which
the problem is that in the formation of any filaments in a plasma, you have that the plasma is going to try and form a minimum dissipation organization of the current. If ohmic dissipation, the resistance of the plasma, is dominant, filaments are not going to form because the minimum dissipation is going to be achieved by spreading the current out evenly. But if the current is sufficient per filament, that hydrodynamic and magnetodynamic dissipation is dominant, then minimum dissipation involves the formation of filaments. And filaments become the minimum dissipation configuration. So that depends on the current in the filament. So since the device has a fixed amount of current, you get more current per filament by reducing the total number of filaments. So that's where we think there might be a problem with our machine, is that due to the actual shape of the teeth, we think that they're actually producing each tooth. So these are teeth on the inner rim of the cathode plate, the field enhancement device. They're producing 2 pairs of filaments per tooth. So we're getting 128 filaments, which is too many. So we think if we just reprofile these teeth, which can be done without creating a whole new cathode, we can reduce the number of filaments and therefore increase the amount of current per filament. Now, if we increase the amount of current per filament too much, we become worried that there will be erosion of the anode by the concentrated current of the filaments. But we don't think that's going to happen if we just get it down to 64 filaments. If we have to get it down to 32 filaments, which this table indicates we might have to, then we might have to worry about the erosion. But in general, we're going to leave the erosion. If we can get the anode to last 1,000 or 2,000 shots, we're going to leave erosion to engineers who would be working on it after we achieve our scientific goals. So our project, the scientific goal, is getting net energy out of the device, more energy out of the device than we put into the entire device. After that, we'll need a much bigger engineering project to make sure we have a device that can last for millions of shots that a generator would have to last through.
All
But
right. Okay. Yeah, thank you, Dr. Eric, for the explanation.
So, Eric, we are looking at very exciting times from your lab. Isn't so?
Yeah, we're excited too, but it's frustrating that we keep getting these delays. As you all know, delays are to be expected in experimental devices. But this anode chose to crack at an inconvenient moment because we were really excited that we were going to get another 2 weeks of experiments with the axial field coil and with different mixes. But we'll have to keep our hats on until the spring when we should be able to do all that. So we'll be keeping everybody informed.
Yeah. There is a kind of feeling always that this kind of a mishap is some kind of a good omen, you know. It tells you that good times are just ahead. Darkness
That's
before
right.
yeah.
Well, especially when it's very clear why the anode failed.
Yeah.
It wasn't a mystery because of the location of the crack. I couldn't get good pictures of it because of depth of focus, but visually it was very obvious that it was due to the electron beam. So at least we don't have a mystery to solve, and we just have a machining delay.
Sure. So could you unshare the screen, please? Yeah. So now we go to my presentation. Okay. Can you see my screen, please? Can you see? Are you able to see my screen?
Yes.
Okay. So I will be talking about a new kind of Z pinch. This is a collaboration between Rajdeep and myself. To give a background, this is elaboration of an idea proposed in the paper, generalized plasma focus problem, and its application to space propulsion, which I published earlier this year. So space propulsion is proposed as a principal application, but there may be many spin-offs such as terrestrial fusion power, short-lived radionuclide factories, or neutron radiography as well. This is actually a repeat of a talk which I gave at the recent ICPCA PSA 2023 conference. So now, what the plasma focus does, among other things, is to provide energy and power density amplification. The plasma focus gathers electric energy stored over a time of several tenths of seconds in a capacitor bank occupying a volume of several cubic meters and transfers it into a time-varying inductance situated inside a vacuum chamber several liters in volume in a time of a few microseconds, and then delivers it to a plasma occupying a volume of few cubic millimeters in a few tenths of nanoseconds. We all know this. The final energy density of the plasma, we know, is found to be constant over 8 orders in stored energy from tens of millijoules to megajoules. So the paper which I mentioned, it develops a first principle scaling theory for a generic class of plasma propagation problems which share many features with the classical dense plasma focus. These are an axis of symmetry, a physical scale length A, which is usually the radius of the central conductor, a gaseous ambient medium of mass density ρ0, a plasma region within the gaseous medium carrying a time-varying current, a pulse power system that supplies the current, a conducting boundaries such as anode and cathode, which maintain electrical contact between the plasma and the current source at all times, an initial surface where plasma formation begins. These are the kind of, if you wanted to make an abstract description of what a dense plasma focus is, this would be the kind of minimum features. In the theory which I mentioned, the boundary and initial surfaces are specified as piecewise continuous algebraic functions. The theory calculates the shape and location of a surface of rotation co-located with the plasma, which is pushed by the magnetic pressure. So the new kind of Z pinch which is proposed, the basic idea is like this. It is a modified plasma focus with a tapered anode that transports current from a pulse power source to a consumable portion of the anode in the form of a hypodermic needle tube continuously extruded along the axis of the device. So this is the anode, central electrode. This is the SREM portion with a constant radius designated by the letter A. This is the conical taper portion. This anode has a cavity inside, and a hypodermic needle tube is continuously is passed from outside to the inside, and it projects beyond the tapered anode. This hypodermic needle tube is a sub-millimeter diameter tube, the tube from which the injections which the diabetic patients use for their daily insulin dose are manufactured. So it is that kind of, so it's a very commonly available manufactured item. So the theory is able to calculate the shape of the plasma. The scaling theory constructed in the paper can be used to calculate the propagation of the plasma focus sheath in this tapered geometry. And this shows an example of such a calculation. This green line here, thick line, is the initial surface of the insulator. This thick black line is the outline of the tapered anode. This is the stem portion, and this is the taper. Beyond the taper, this red line is the hypodermic needle tube. You see these curved solid lines. They are the cross section of the surface of rotation, which is co-located with the plasma in the scaling theory. And what it shows is the propagation of that surface as along the anode. The sheath is seen to strongly accelerate as it crosses the tapered portion. You see, all of the distance between the lines keeps on increasing as you go along the anode. This figure shows a detailed view of the hypodermic needle tube portion. You see that the surface is very strongly curved. This is because the current is flowing from the anode in the hypodermic needle tube and returning via the plasma here. And the magnetic field is changing as 1 over r square. Magnetic pressure is changing as 1 over r square. And so that is quite rapid. And you can see that this surface, the calculated surface, is very strongly curved. The theory can also calculate time variation of inductance and current, and we shall see examples of this quite soon. So the hypodermic needle tube, which I shall refer as HNT, with an outer diameter of just 160 microns and inner diameter of 50 microns, is filled with a gas which could be hydrogen, deuterium, or xenon, or argon at several bar pressure, not millibar, several bar pressure, and it could also be filled optionally with an axial magnetic field. The current from the capacitor bank flows from the anode into the HNT and it returns to the cathode via its contact with the plasma focus sheath when it sweeps over it. Now, remember, it is the contact with the anode is permanent, but the return current is moving. The return current path keeps on moving because it is a plasma which is returning the current to the cathode. So until the plasma focus sheath reaches the end of the taper, the HNT is not aware that a plasma is going to visit it. So the HNT explodes only after the sheath reaches it. Till then, it remains decoupled from the capacitor bank. So the same HNT can be used in a few kilojoule proof of concept system and a few megajoule technology demonstration system. So the energy density of the plasma, which is formed inside the hypodermic needle tube, should scale with energy. Unlike that in the plasma focus case, where the energy density of the final plasma is constant over 8 orders in stored energy. So this idea combines useful features of many Z-pinch concepts. Power density amplification as in a plasma focus, as I mentioned deliberately. Initial axial magnetic field as in magnetized liner inertial fusion, that is maglev. Wall stabilization as in the HDZP, high density Z-pinch. Radiation trapping as in a Z-pinch dynamic hold-on. Compression of magnetic flux as in a stage Z-pinch. So all of these things have been discussed in literature. There are examples, but some features of these are present in a new manner in this idea. This idea is scalable with a first principle based scaling theory. Now, this first principle based scaling theory, I wish to emphasize because this scaling theory has been fully derived and with the expectation that anybody interested can rederive it for himself and confirm that there are no hidden assumptions, that everything is transparent. The scaling theory has a built-in optimization procedure for maximizing maximum energy transfer. More importantly, a proof of concept experiment is feasible using the UNU ICTP plasma focus at NTU Singapore. So this is the kind of the focus of the collaboration which Rajdeep and I are exploring. This is just a concept at the moment. We are just exploring the idea, and that's all. So let me say a few words about this proposed proof of concept experiment, which is being evaluated at present. It's just at an evaluation stage. It is based on the UNU ICTP plasma focus at NTU Singapore. It is just a single capacitor of 30 microfarad charged to 14 kV. It has measured inductance of 110 nanohenry and a static resistance of 12 milliohm. The proposed experiment has a stem radius of 16 millimeters, a cathode radius of 50 millimeters, a stem height of 45 millimeters, taper height of 120 millimeters, HNT plus end cap height is 25.4 millimeters, insulator radius is 10 millimeters, insulator height is 30 millimeters, and HNT radius is 80 microns. The fill gas is hydrogen at 6.5 millibar. So this figure shows the calculated dimensionless inductance during the propagation. So the blue portion corresponds to the propagation in the stem region. The red corresponds to the propagation in the taper region, and the green corresponds to the propagation in the hypodermic needle tube region. So this is the calculated current from the proof of concept experiment. The vertical axis is current normalized to I0. I0 is the charging voltage divided by the capacitor bank impedance. And the horizontal axis is the time normalized to the quarter cycle time, which is 2.8 microsecond for the NTU, the UNU ICTP plasma focus at NTU. Now, this device is designed from this theory so that there is a maximum energy transfer when the plasma reaches the end of the taper, just before it begins to slide over the HNT. Its energy in the dynamic inductance is maximum. So the kind of current which we are talking about is about 150 kiloamperes at the end of the taper, which is about 65% of I0 and 75% of the maximum short circuit current which the capacitor bank is capable of giving. So these are theoretical maximum values which cannot be exceeded even in principle. So these are some of the scaling theory estimates for the proof of concept experiment. The current at the base is 153 kiloamperes at the base of the taper and 148 kiloamperes at the end of the taper. The magnetic field, B theta, is 1.9 Tesla at the base of the taper and 373 Tesla at the end of the taper. The velocity of the sheath calculated, that is the surface, on the surface of the electrode, is 50 kilometers per second at the base of the taper and 1,000 kilometers per second at the end of the taper. The electric field at the surface of the electrode is 100,000 volts per meter at the base of the taper and 4 billion volts per meter at the end of the taper. For this velocity, which is 1,000 kilometers per second, the kinetic energy of protons in the sheath is expected to be 1 MeV. The sheath crosses the 25 millimeter long HNT in 2.5 nanoseconds. The effective DIDT of this would be 5 × 10⁻13 amps per second. For comparison, the Sandia Z machine puts 18 megaamperes of current into the Z pinch load in 100 nanoseconds. So that makes effective DIDT, average DIDT, which is just 3.6 times higher than this value. So continuing with the highlights of the scaling theory estimates, the partition of energy at the end of the HNT, not at the end of the taper, when the plasma has crossed the HNT, the total stored energy is 2940 joules. The magnetic energy coupled with the static inductance is 1057 joules. The magnetic energy coupled with the dynamic inductance is 550 joules. Resistive dissipation is 284 joules. That remaining in the capacitor is 125 joules. The kinetic plus internal energy is 924 joules. The magnetic energy in the dynamic inductance is ultimately dissipated within the HNT mass of 3.5 milligrams, which is about 150 megajoules per kilogram. So what kind of phenomena do we expect within the HNT? This is based on already known work from other authors. First of all, a strong converging shock wave driven by a nonlinear magnetic diffusion wave propagates in the HNT material. On reaching the inner free surface of the HNT, an ionizing shock wave driven by a magnetic piston is launched in the fill gas. The shock wave reflected from the axis collides with the incoming magnetic piston to form a Z-pinched quasi-equilibrium. The pressure built up on the axis because of the shock wave is relieved by axial outflow. The radial transit time is much smaller than the axial transit time, so a radial pressure quasi-equilibrium is established over the intermediate time scale between the radial transit time and the axial transit time. The metal plasma continues its implosion and compresses the B theta magnetic field as in a staged Z pinch. The mass per unit length of the HNT is conserved during this implosion, this is just the cross-section area of the hypodermic needle tube multiplied by the mass density. So its conservation means that the velocity of the inner surface, which is the rate of change of the inner radius, varies inversely as the inner radius. This is a very well-known thing. So as the inner radius approaches the axis, the inner velocity diverges. This is the same principle which is used in inertial confinement fusion targets to achieve a fusion spark, which is supposed to begin the ignition of the ICF pellet. Now the velocity of the outer surface, which is there in the numerator here, is governed by the equation of state of the HNT material, the current flowing in it, and the radius of the HNT, the instantaneous radius of the HNT. The velocity of the inner surface increasing rapidly during implosion because of the convergence effect, which is the inverse dependence on the inner radius. So this figure schematically describes the terminal phase of the HNT implosion. The gray is the imploding HNT. The red is the plasma pinch. And yellow is the magnetic field which is separating the two. The yellow magnetic field portion is acting as a soft pressure transmitting medium between the imploding metal plasma and the hydrogen pinch formed by the gas which is inside the HNT. So in the terminal phase, when everything comes to a standstill, all the pressures must become equal. So this is the momentum flux density. This must equal the magnetic pressure and plasma pressure, which is equal to this, the temperature, the final temperature of the gas which is produced in the pinch, or the plasma in the pinch. Now, this relationship can be used to estimate the final temperature of the plasma inside the HNT. So we try to, this figure indicates the maximum temperature of deuterium in the HNT calculated from that formula. Now, the first curve, which is blue here, corresponds to 138 kiloamperes. This is the current in the proof of concept experiment simulation at the end of the, when the plasma is crossed the HNT. You look at the vertical axis here, it is temperature in kilo electron volts. It is 500 keV, 1000 keV, goes all the way up to 3000 keV. The horizontal axis is deuterium pressure in bar, 2, 4, 6, 8, and 10 bar. So at 5 bar of deuterium, somewhere in the middle of the axis, the final temperature is expected to be about 25 keV. So the proof of concept experiment can realistically hope for significant fusion yield from DD as well as P11B reactions. Now, notice here the scaling. This is 500 kiloampere curve, this is 800 kiloampere curve, and this is 1000 kiloampere curve. So these temperatures are going into 1000 keV region. So we are talking about the possibility, looking at what should happen if this POC experiment works, and then what kind of scenario should be expected after scaling. So these are some of the upscaling scenarios. The POC experiment is designed for maximum energy transfer at the end of the taper, which we already saw that the current is already 75% of the maximum current which the capacitor bank is theoretically capable of giving. So the scaling theory shows that the normalized current profile remains invariant if all the geometrical dimensions as well as the capacitance, inductance, and voltage are all increased in proportion to the stem radius. So here we see this is the proof of concept experiment with the stem radius A is 16 millimeters. This is twice x, thrice x, 5 times, and 10 times. The voltage is 14 kV, 2 times, 3 times, 5 times, and 10 times. Capacitance is 30 microfarad. It is increased twice, thrice, 5 times, 10 times. Inductance is 110 nanohenries. It is increased twice, thrice, 5 times, 10 times. The current at the end of the taper is 148 kiloamperes. That also increases twice, thrice, 5 times, and 10 times. The magnetic field at the end of the taper is 370 Tesla. That also increases in the same proportion, twice, thrice, 5 times, 10 times. But to reach that, look at the energy. Here it is 2.94 kilojoules. here for 2x, it goes 8 times. For 3x, it goes 27 times. For 5x, it goes 125 times. For 10x, it goes 1000 times. It scales as the cube of the linear scale-up factor. Now, this concept has some special features for space propulsion. The plasma focus sheath and associated magnetic field act as a magnetic nozzle to maximally convert thermal pressure into axially directed impulse. A non-nuclear engine is possible with a non-fusile gas. I'm talking about xenon or argon, something like that, or hydrogen. The implosion of the HNT has a conical shape because the end nearest the anode begins implosion earlier than the far end. This can generate a jet at the axis with a velocity much larger than a terminal implosion velocity. This is a very well-known effect. Russian literature calls it the cumulation jet, and in Western literature, it is known as the Monroe effect, which is the basis of armor-piercing projectiles, artillery. So, with an inner lining of solid decaborane, I'm following Eric here. This jet could reach sufficient proton velocity to achieve avalanche P11B reactions, providing an aneutronic interstellar engine. So I end my talk with a summary. A new kind of Z-pinch has been proposed as an aneutronic scalable space propulsion engine. It combines beneficial aspects of many well-known Z-pinch schemes. Preliminary considerations show that it should be possible to construct a proof of concept experiment by modifying the UNU ICTP plasma focus at NTU Singapore. And this POC experiment would aim to validate the scaling theory, generate operating experience, and gather data required for its future upscaling. Thank you for your kind attention. I'm open to questions now.
Yeah, Sunil,
Yeah.
Eric.
Yeah.
I mean, have you considered the materials aspect? In other words, if you're tapering down essentially to a point,
Yeah.
you're going to have a lot of pinch forces on that, and you're also going to have a lot of heating.
Yes.
So have you considered what sort of material you'll need to survive at that tip? Because I think that if you get, I mean, the rule of thumb that we've been using is about 1 megamp per centimeter of radius, which we haven't reached yet.
Yeah.
But it seems to me if you're going to, at that tip, go way beyond a megamp per centimeter of radius, then aren't you going to have enormous erosion? The tip isn't going to last very long.
Exactly. So, Eric, I would like to quote you saying that that would be something, for the engineers to bother after we show proof of concept. But there is one thing I should make clear, that the anode is supposed to be consumable. So if the HNT definitely is consumable, it is designed to be continuously extruded. So perhaps even the portion of the anode which is getting eroded, that also could be replaced or extruded perhaps more slowly. But that's you see, this is the difference between energy producing machine such as what you're considering and a space propulsion engine. So there is a space propulsion engine is meant to consume material. So I think that is the difference. Louis?
Yes, sorry, I was
Yeah.
looking for the for the microphone. Okay. No, my question is about the confinement time of this. No, because this, of course, will depend on the inertia, no, of the imploding material. Because if you may have with the same energy, I mean, no, you can accelerate more mass, no, at lower speed, or no, I mean for the needle, no, not for the plasma form. I didn't get the point of how about the confinement time expected or something like that, or duration, no, of the confinement, no, at the time of.
Yeah, you see, that is the reason why this is not a fusion reactor. This is a space propulsion engine. We do not want to confine it. We want to eject it. Our whole idea is to make a hot plasma, as hot a plasma as we can make, and eject it as rapidly and as efficiently as possible.
Okay.
You see, now, suppose, you see, so this is not that. So we are not aiming at any kind of Lawson criterion or any kind of scientific break-even. We are just trying to, efficiently propel mass at the maximum possible velocity. You see, the significance of this is, don't think about what is going on right now in space travel. People are trying to already talking about making a moon base, Mars base, serious people with serious money and serious, planning and governance behind them and all that. Now, sooner or later, they are going to require a spaceship which delivers a lot of cargo before the human beings reach there, right? So what is needed is a spaceship that, for putting 10 tons of cargo, it should not require 100 tons of fuel. So basically, we need to have something which accelerates a small amount of mass to a much higher velocity. So that is the basic idea, behind this kind of concept.
Yes.
But of course,
yeah.
but suppose it so happens that this also produces fusion reactions efficiently. We don't know, right?
Yeah.
This is too early stage. But so just think of it. If suppose this does happen to produce fusion energy, what you do is ejected jet which is coming out, right? You direct it into say liquid bismuth or liquid lead, something liquid metal, and heat it and drive a convection loop and make it into a MHD power station. So not very far-fetched from a reactor, from a terrestrial fusion power reactor point of view, right? And suppose it does happen to produce neutrons. So, okay, use it for a neutron radiography. It will be a sub-millimeter, sub-nanosecond intense neutron source. Yeah, it would be very good for a neutron. You see, you look at the kind of facility which is being built by Andrea Schmidt's group in Lawrence Livermore. That is for neutron radiography. But that's a 50 nanosecond duration source with few millimeter diameter. We are talking nanoseconds and sub-millimeter. If it works, we don't know. But It is at the stage of an
Yeah.
idea. It is at the stage of an idea under evaluation.
Yeah. Is a future spaceship, you know,
Yeah.
will be to start the trip outside the terrestrial, I mean, gravity, no, because you have no too much power, no, for doing from the I don't know how this will work, but it's a very interesting idea. No? I guess that the initial plasma focus was based on some kind of a spaceship purpose. This kind of I mean, I don't remember exactly, no, but I mean the very beginning of the plasma focus. The idea was to accelerate ions or something in order to use as a.
No, it is still there.
I don't know if Eric has something to say.
Actually, that space propulsion is being used, you know, but it is being used for satellite navigation and satellite positioning and this kind of a thing. I don't know, Leopoldo is not here, but he's working on such things.
Yeah,
Okay,
so
thank you.
Yeah,
We
Eric, you
were-
wanted to say something?
yeah, I just replying, we were funded by Jet Propulsion Lab at a very minimal level back in the 90s for
Okay,
using the plasma focus for space propulsion.
okay.
So unfortunately, the program that was funding us got abolished by the Bush administration. So that ended, but NASA has had, you know, historical interest in using the plasma focus and other plasma devices as propulsion.
In fact, they still do. They still are having a program. You see their. I think I cited one of their papers in my paper. They are still interested. Any other questions? If there are no questions, shall we go to the next presentation by Sasha? Sasha, are you there? Sasha? Sasha? Sasha Blagger?
Share screen.
Yeah, please share your screen.
I'm trying to share my screen.
Okay.
Share screen. Okay.
You click on the application, your PPT. In the share screen window, you will see your open PPT. No, not this. No, you go to again share screen
Yes.
and look at your PowerPoint presentation. Search for your PowerPoint presentation in the screen, in the share screen.
Do you see it?
No. Maybe you unshare and again share.
Stop sharing.
Yeah. And now when you press the what is this? Serious Seeds. Who is interested in a strawberry banana smoothie?
Wait a minute to go.
You are sharing the full screen, not the part of that.
No, no. Oh,
This is the full screen, I mean.
Full screen. Just a moment. Oh, full screen. Oh, I have. No.
I think you
no.
close. You should close your other windows so that leave only your PPT window.
There are a lot of windows open here.
Now, what you do is you on your bottom taskbar, whatever open windows are there, those you close. Only leave the PowerPoint.
Our yes, just a moment.
You close all those windows.
Yes, just a moment. Still. There it is.
Oh, yours is a Mac.
Mm,
Yours is a MacBook.
mm. Oh,
No. Why are we seeing Alan Bernard's screen?
okay, so you have the cat, and
Alan?
the cat, Giovanni, here. Close, only close. Is moving away from. Don't see. Secretary. Oh, I'm sorry.
Can somebody guide? Paul, can you guide him?
Applications. I
What seems to be the problem?
cancel.
He's not able to share his. He's not able to open his.
Let's not share that video. No.
You are sharing your screen, but you are just sharing your web browser.
Do you see something now?
I see your web browser. Maybe you close your web browser.
You close the web browser. Yeah, I think so.
This one? No.
So
I'm
I
seeing.
see.
You close down here. You close down here. You close on the here.
Okay.
This one you close.
I'm seeing my presentation now, but you didn't see here, right?
You have no.
Maybe try again.
Yeah, please try again. Close down your browser.
Lost my brother. But if I close, I will go out from the from the meeting.
Maybe you try to click share again at the bottom of the Zoom meeting screen.
Share screen, yeah.
Yeah. Oh, подерли.
Yeah, when you select the share screen, there's a window pop up which shows whether you want to share screen 1 or screen 2 or one of the windows.
Oh.
Paul, can you share your screen and show him how it looks?
No.
No, I don't think that's possible.
When I try to share, just a moment.
When you click on share, you should see a window pop up. And in that window, you should see several other things which you can select which to share.
Yes, here I'm pressing this sharing.
So on my PC, it says screen 1, screen 2, or then, and it shows some of the windows like the web browser or the PowerPoint.
This one? Do you see it?
Yes. Now it is there. Yeah. Now what you do is
yes. Okay. Okay.
Now
you click on this one. Yeah.
Okay, now it is there. Good.
So you can see the title of this talk from Dr. Aluk, Dr. Yordanov, and myself. First experiment looking at the symmetry of the plasma formation phase of dense plasma focus using D-dot probes. So background, dense plasma focus is proposed as the basis for any energy propulsion machine. We hear just now energy producing machine, a space propulsion engine, it was previous talks, and technology for making materials for novel properties. Ensuring a reliable and reproducible operation of this device have some challenge so far. It does not operate well immediately after exposing the PF machine to open the PF, exposed to the atmosphere, and re-evacuating. A series of training shots required, after which the operation stabilizes until the vacuum is opened again. This phenomena has remained poorly understood so far. Our previous work on numerical simulation of the formation of the formation of the breakdown of in PF machine show that plasma behavior on hydrodynamic time scales is difficult because of simultaneous presence of many time scales and systematic understanding of the role of training shots process, therefore requires a new experimental approach. We present the first experiment looking at the symmetry of the discharge during the formation phase using D-dot probes. So here are a picture of our PF machine. Here is the electrode system with removed upper part of the chamber, and here are the electrodes, and here are these probes, 3 of them. This picture show the same plastic tube with this part which is fastened to the plastic tube. This is commercial SMA adapter. We are cutting these 4 horns and cutting half of the central pin, fastened with epoxy this detail, and cover with a thin layer of silicone. So this is the head of these sensors. Here is the picture of our PF device, chamber, well known, capacitors, vacuum spare gaps, oscilloscopes, charger. Oh, it disappeared. Oh, yes. The next slide is principal operation of the D-dot probe detectors. I don't know. Do you see this central?
Yes, yes.
One? The central conductor of the of this sensor is looking at the PF anode through a gap between the cathode rods. The SMA connectorized cable is connected to the oscilloscope through a cable in its characteristic impedance of about 50 ohms. Time varying voltage of on the anode or a plasma in the insulator is proportional to the displacement current to flow through the capacitance between the conductor of the SMA adapter and the PF anode. The current, this displacement current ID, equal to the rate of change of the electric displacement, produce an oscilloscope signal of voltage IDZD. This is well-known D-dot probes. The detector is sensitive only to the plasma between the active plasma on the detector and the anode. The sensitivity depends on the geometry of each placement. We present below our first results. We demonstrate that the detector produce physical significant signals. This experiment is first of this kind. Therefore, our priority is on refining the technique by developing calibration procedure for interpreting the results. And this is the first slide. Here we have the by dt curve, and the first D-dot probe, red line, probably is not operating okay. The this
So
green.
you click on the
Oh,
click left click. Click with the mouse. Click left click. Okay.
yes. This 3-dot probe is cut it. It's too sensitive. It's more sensitive of all these D-dot probes. And here on this slide, it is cut a little bit here and here. You have to think in mind that I used several types of the D-dot probes, starting with the sensitive part of 5 millimeter diameter. This was detail which Sunil made and sent to me, and now the sensitive part of this D-dot probe is upper. The diameter of this sensitive part is 1 millimeter, and the signal is still too large. Here, the second D-dot probe showing some structure, and here there is a 0 parts of and this show that probably here maybe it's seen on the next slide.
You click on that. Left click.
Да, така, D-dot hazard, така. Looks like a plasma here is not already not in front of the probe, and here probably is starting the rundown process. This is the next shot. Here, both second D-dot probe and third one here they have yes, they have different shapes, and therefore we need additional cross calibration in order to analyze this signal. So this D-dot probe tube is showing have 0 regions just before the dip of the DI by the signals and after it. Okay. I think I show already this thing. Maybe I
No, this is the next shot.
Next shot here. Here we have some structure. So maybe we have multiple seed formation, probably. No, here the D.3 and D.2 have similar structure. It shows that formation of the plasma is not fully symmetrical. And these flat regions probably show that this is beginning of the rundown. Discussion. This example demonstrates that the detectors respond to physical phenomena. in situ cross-calibration of the detector is being attempted. This show whether differences in detector signal are a result of non-physical response, probably displacement error or plasma asymmetry. This diagnostic appears to show that beginning of the rundown phase is important for generating data on the dependence of plasma formation time on gas, dependence of the plasma formation time on gas pressure and species. Plasma backflow after the pinch disassembly appears to be I cannot read from this picture here. Yes, appears to be it's from behavior of the D-dot signals show that yes, show the behavior of the plasma both from the period before the pinch, during the pinch, and after the pinch disassembling of the plasma. Okay, so conclusions: we are developing a new diagnostic then can potentially help us to understand the plasma formation dynamic under varying conditions. First results show that the diagnostic respond to physical phenomena. There are also important questions that must be answered by technical improvement and more extensive data collection. So, thank you for the attention. I'm sorry for this very confused talk, but it's for the first time for me to do it online. So, thank you.
Yeah. Okay. Can you unshare and unshare your screen and switch on your video?
Okay.
So, okay. Any questions? Any questions? Sasha, can you put on your camera?
Just a moment. The video mute. Camera. I cannot see the icon. Start video. No.
The left hand bottom corner. Okay, now I can see you.
Bottom.
Yeah. Okay.
Yeah,
There's a question from Louis. Louis, can you please ask your question?
Yeah. No, just a question about if I don't know if this in this case it's possible to have some capacitance coupling or something like that. You know, magnetic proofs according to the position. Sometimes you have some, for example, no, I mean, and you have some capacitance coupling, no, because you have metals, conductors, and very close or something like that. My question is if this, in this case, this is possible or not.
Well, I would like to answer your question. Basically, this D-dot probe is a capacitive probe. When the capacitance is the probe. So, yes.
Yeah, yes, but an extra, not considered. I mean.
Yeah, okay. A spurious capacitance, unwanted capacitance. Okay.
Yeah, yes. Sometimes there is some extra that modifies the measurement.
This is in fact the technical problem which Sasha and we have to solve. You see, this is being put between the two cathode rods. So the cathode rods will also put some capacitance, as you said, right? So if there is so that could be that could cause a difference in the response of various detectors. Okay. So now that is one thing. Other possibilities are, well, there are always, this is the first time it is being made, and this is done in a kind of, it is still an ongoing work. So we have to get the skill required for the proper placement of these things. Right now, this is done just by hand. You drill 3 holes in a plastic tube. The plastic tube is too big. It is not close fitting to the cathode. So a proper mounting of that probe is definitely the next step to do, and that should address your question. Okay.
Thank you.
So,
yeah, that's very interesting and difficult problem is to fix all this.
Yeah. So, Kang Yusung.
Hi, I just have a question with regards to the D dot probe. You mentioned that it was connected to a SMA, and then you said that that would then be connected to an oscilloscope, right? And then in one of the slides, it says that with 47 ohms. What is that 47 ohms referring to? Is it to a wire? Is it to an impedance or something like that?
Well, the cable, you see, the whole diagnostic has 3 parts. One is a elbow-shaped SMA adapter, which is fixed outside the cathode. That is one part. Second part is a cable which has the mating connector, that is a SMA connector, on one side. On the other side is a connector which goes to the oscilloscope, and that has to be terminated in the characteristic impedance of the cable, which is the 47 ohms, which is nearly 50 ohms. So it's a 50 ohm coaxial cable. It has to be terminated in the characteristic impedance. Otherwise, you will have oscillations. Does it answer?
Okay, got that. Yep, thank you.
Yeah. Wahid.
Yeah, hi.
No, you're Roshan.
Just,
You're Roshan.
yes,
Yeah,
yes.
okay.
Yes. Just one question. Is it possible to put the D dots on the anode itself to do some measurements? Is there any problem with that or what?
No, I couldn't get your question. Can you put on your camera?
The detectors on the anode itself.
No. Anode is the thing which is being, it is the anode, it is the capacitance between the anode and a floating conductor, which will develop the voltage. So basically we need a floating conductor which is sensing the electric field which is being emitted by the anode. So it doesn't make any sense to put anything in contact with the anode. That would be resistive. And that would have to, have the high voltage isolation, and it should absorb all the energy. That is what normal resistive voltage probe does. So we are not doing that. The main idea here is the geometry of the probe is such that unless the plasma is directly between the active area of the probe, which is 1 millimeter diameter, and the anode. So it's a very narrowly defined kind of tube. Only if the plasma is within that tube, you will see a signal. If the plasma goes out of the tube, you will not see the signal. Okay. So it is a spatial resolution which we are getting by this construction. By kind of putting it in contact with anode will not serve any purpose. Does it answer your question?
Yep. Okay. Thanks.
Yeah, any other questions? Anybody else? So Sasha,
Yeah.
we continue with our work.
I beg your pardon. Could you repeat?
Yeah. So far we are doing good, but we continue our work, right?
Yes, yes, of course.
Yeah. Okay. So that brings us to the end of our all the presentations. So thank you everybody for attending this workshop. I hope it was fruitful and informative. And so anybody else wants to make anything? I want to thank Paul very much for stepping in to help us organize this. Thank you, Paul.
Thanks. No problem.
Yeah. And so I wish everybody a Merry Christmas and a Happy New Year before we meet again. Okay?
Happy New Year.
Thank you
Thank
very
you.
much.
Thank you.
Okay.
So we close the meeting now. Okay?
Yeah, happy New Year
Yeah,
and
bye.
bye-bye.
Bye-bye.
Happy-
Bye.
Yes, yes, yes.
Bye-bye.
Bye-bye.
Right.